Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today, we have the pleasure of receiving Benjamin Florentin from the Institut Elie Cartan de Lorraine, who will tell us about Steklov spectral inverse problem in a conformal class. As usual, if you have a question during the talk, either ask it in chat and we'll relay to the speaker, or unmute yourself to ask it directly. Benjamin, the floor is yours.
Thank you. First of all, I'd like to thank the organizer for the invitation. It's a real pleasure. So today we will focus on the inverse problem for the Steklov spectrum, which can be seen as the analog of the question, can one hear the shape of a drum, formulated by Kak in the 60s. So I'll start by recalling the problem. Then I'll give a few useful reminders of basic microlocal analysis. And I'll state the Duistermaat-Guillemin trace formula, which is the fundamental tool used here to exhibit interesting spectral invariants. This technique is, of course, one of the main tools that we have for attacking these kind of spectral inverse problems. And it has been used quite extensively for the Laplacian spectrum. Okay, to conclude this presentation, I will take the time to present some results obtained in the case of conformal metrics, and in particular, a boundary determination result. So let's recall the problem. We are given a smooth, compact Riemannian manifold with boundary, and we're interested in the Steklov eigenvalues problem, which is an eigenvalue problem with the spectral parameter in the boundary conditions. So it consists in finding scalars sigmas satisfying this, of course. And since we have a compact manifold, the scalars form a sequence of eigenvalues with some multiplicity, and which can be ordered in this way. So equivalently, one can consider the eigenvalues of the usual Dirichlet-to-Neumann map, which is of course a linear operator mapping a potential f at the boundary onto the normal derivative at the boundary of its harmonic extension. And okay, we will use the notation, this notation for the multiset of these eigenvalues here. And we are interested in the inverse problem. Okay, so can one recover a metric G up to of course up to a natural gauge invariance from its Steklov spectrum? Okay, this is the analog of the shape of the drum, the Laplacian spectrum. And just as the Laplacian, the answer is no in general. And you have a lot of negative results, of course. Okay, there are two main techniques known, which are adaptations of techniques developed for the Laplacian spectrum. So the Sunada's technique and the torus action method. Okay, since our goal here is to get some positive results here, I'm not going to spend too much time, and I will refer for the Steklov spectrum to the work of Gordon, Erbrich, and Webb from 2018. They have worked hard on this topic, and the literature is pretty large at this point. I can mention that one can also make it by direct computations. For example, Colbois, El-Soufi, and Giroir in 2017 shows then that cylinders over Laplace isospectral closed manifold are also Steklov isospectral. Okay, so I will continue with a few reminders of basic microlocal analysis. To fix IDs, we consider an open set of Rn and define a pseudo-differential operator. So this is a linear operator of this form. with the function p here, which is called a symbol, and it is in the class, this class of symbol SM, so pretty standard. These symbols can be thought of as generalized polynomial functions in the Xi variable. And one can define the class of smoothing symbols, S minus infinity, corresponding to symbols decreasing faster than any polynomials. And in the symbolic calculus, they are negligible. And we have a quantization map, of course. So defining a pseudo-differential operator, you take a symbol and you have a pseudo-differential operator by this procedure. And of course, differential operators are also pseudo-differential operators. In particular, they correspond to take polynomial symbols in the Xi variable. There is an important class of symbols which are the polyhomogeneous symbols, and which admit asymptotic expansions like that. Okay, you have this decomposition of the full symbol as a sum of a positively homogeneous term. Okay, so this is equivalent to that. This symbol, this asymptotic symbol, so pretty standard, but for all n, you have this, for all degree n, you have this decomposition of the full symbol when for Xi large enough. Okay, so these symbols can be thought of as the closest to polynomials in Xi, and the corresponding pseudo differential operator, called classical pseudo differential operator, are those closest to differential operator. You know, you have a symbol calculus and symbolic calculus. And yeah, you can, roughly speaking, you can manipulate the symbol just as differential operators. And a note here is that if you have the same asymptotic expansions, then you, of course, the full symbols coincide modulo a smoothing symbol. And the classical pseudo differential operators associated are coincide modulo a smoothing operator, which maps function into smooth functions. Okay, it's negligible in the microlocal analysis. So of course, we can consider the setting of closed manifold and then symbols acting on the phase space, which is the cotangent bundle. And in the same way, one can define polyhomogeneous symbols. So in any coordinate chart, you admit this expansion. And what's interesting about that is one can read the principal symbol of a classical pseudo-differential operator as the highest order term in this expansion. And also one can define another invariantly defined quantity, which is called the subprincipal symbol. And we have also an explicit formula here in the coordinates. So roughly speaking, it's the homogeneous term of order m-1, and from which this term has been removed to make this quantity invariant to coordinate change. Okay, and also we can see the principal symbol as an Hamiltonian, of course, an energy, and the associated Hamiltonian flow is called the bicharacteristic flow, and of course it preserves energy level hypersurface. So, for example, the Laplace-Beltrami operator, which is an elliptic differential operator of order 2, with principal symbol given by this norm on the cotangent bundle, this square, the norm, the square of the norm. And here the subprincipal symbol is 0 for the differential, for the Laplace-Beltrami operator. So you can do explicitly the computation, or you can say that this is a differential, a self-adjoint differential operator with a real coefficient. So its subprincipal symbol is 0. Important fact. And the bicharacteristic flow associated is, of course, the geodesic flow, acting on the unit cotangent bundle. And another operator, interesting operator for us, of course, is the DN map, which is a classical elliptic pseudo-differential operator of order 1 this time. And this is a perturbation of the square root of the Laplacian on the boundary. Here, this G is the metric induced on the boundary, and B is a pseudo-differential operator of order 0. So you have this decomposition, and consequently you can read the principal symbol is just the norm on the cotangent bundle, just as here, this is the square root of the principal symbol of the Laplacian on the boundary this time. And this time, the subprincipal symbol is not 0. This is an important observation here for what we will see. And it is given by the principal symbol of B. And we can actually compute this principal symbol in coordinate. And of course, the bicharacteristic flow associated with the DN map is also the geodesic flow acting on the unit cotangent bundle, but of the boundary. So now we want to look for spectral, to attack this problem. We want to look for spectral invariants. This is the usual way to do that, to attack this kind of problem. And to make that happen, there are different functions constructed from eigenvalues, and that we can use to exhibit spectral invariants. Here we will focus on the wave trace, so wave trace invariant. So what is the setting? So we consider a smooth, compact Riemannian manifold, and of course the DN map is a pseudo-differential operator acting on the closed manifold, which is the boundary. So to use this formula, this result of Duistermaat-Guillemin, you have to consider closed manifold, and okay, I won't go into too much detail. These are profound results, and there is a big machinery involved. But let's just give the principle. And note that the work of Duistermaat and Guillemin is much more general, since it considered the spectrum of any elliptic, positive elliptic pseudo-differential operator. So it's much more general than the DN map, actually, or the Laplacian. But I have to mention that these results that I have that I will present were already known for the Laplacian. By it had been established by Colin de Verdière and Jacques Chazarin just after that, and previously to the work of Duistermaat and Guillemin. Okay, so now the principle, we consider one can form, knowing the Steklov spectrum, which is discrete, one can form the spectral distribution and take its Fourier transform. And actually, when you compute it, it turns out to be the trace of the wave group, which is a one parameter family of unitary operator given by the Stone's theorem. You know, you have this 1-1 correspondence between a self-adjoint operator like the DN map and and unitary group like that. So you can form these wave group. And okay, the first result due to Ormander and its Fourier integral operator theory says that the singular support of this trace is contained in the set of periods of periodic geodesics of the boundary. So once again, it's much more general than that, of course. As I said, if you consider a general pseudo-differential operator, this is you said that the singular support is contained in the set of periods of periodic bicharacteristic. So integral curves for the Hamiltonian float associated. And so to do that, you have to notice that okay, that the for each t, this u of t is a Fourier integral operator, and and then you have to use the Fourier integral operator theory, because when you know that it is a Fourier integral operator, you can actually know how the singularities move, you know, and it moves along the flow. Here the geodesic flow. So this is essentially the proof. So you can compute the waveform set, which is the singularities in the phase space, and then project to get the singular support. And you have this inclusion, because it's not trivial, but it's due to Ormander. So okay, but the question is the other inclusion, and this is the hard work. I mean, made by Duistermaat-Guillemin, and before that Colin Verdière and Jacques Chazarin for the Laplacian. And this is done by establishing a trace formula. So I gave a version of that for the DN map. So we consider also a smooth compact Riemannian manifold with boundary, okay, and the boundary, which is the closed manifold that we consider. So we suppose that it admits a finite number of periodic geodesics of a period t, you know. So if you want to show the other inclusion, you take a period here, and you want to show that it is a singularity. So which with this expansion here, you can see that it is a singularity if there is no cancellations here. You know, if this term turns out to be 0, then t is no more singularity, and so you have to make sure that it does not happen. And so the formula first. We have to suppose some non-degeneracy conditions on the geodesic, okay? But the important thing here is that the leading term is given by this exponential term here of and the quantity, the important quantity here is the average of the subprinciple symbol of the DN map over closed geodesics. And what we can notice is that for the Laplacian, this term doesn't exist, you know, because we have said before that the Laplacian has a 0 as the subprinciple symbol of the Laplacian is 0. So this term doesn't exist, okay? And you have no more information. Okay, so to exploit that, to be able to exploit that, to attack the inverse spectral inverse problem, we have to you know, to make sure that these cancellation does not happen. And to do that, we usually consider the simple length spectrum assumption, which consists to ask that all periodic geodesics have different length. And actually, this is a generic condition, so it's not so it's pretty it's more acceptable, let's say.
But it's very hard to check for any given example.
It's very hard to
check for specific examples.
Yes.
It's generic, but in a very weak, bare category sense.
Yeah. I agree. Okay, good remark here. Okay, but in the sense of bare, of course, generic condition. And so what we can what we get here is that if we suppose that the boundary, so the closed manifold, but here we work on the boundary. If we suppose that this boundary is Anosov, with Anosov to guarantee this non-degeneracy condition here, which is equivalent to say that this quantity here in the denominator is non-zero. Okay, and the Anosov property plus the simple length spectrum property assure that it consists in taking R is equal to 1 here. So you have just one term here, and of course you have no cancellation here, and you can say that you have the other inclusion. And another point to notice is that for the Laplacian, the difference with the Laplacian is okay. Also, if the manifold is Anosov, you have also this term, the Morse index, which is 0. Okay, so this term disappears because you have no conjugate points, and also for the Laplacian. For the Laplacian, this term doesn't exist because, as we have said before, the subprinciple symbol of the Laplacian is 0.
So in that case, you don't need the simple geodesic, the simple assumption?
Yes, exactly.
Okay.
So in that case, yeah, it will be my last remark. Exactly. This is for the Laplacian. The main difference is that for the Laplacian, you don't need the simple length spectrum assumptions to get actually this result, which is the fact that the Laplacian the spectrum determines the length of periodic geodesics. So to get this point for the Laplacian, you don't have to consider the simple length spectrum by this remark assumptions. But for the Steklov spectrum, you have to because you have this term here. So on the one hand, you have to add this assumption, okay, to be able to exploit this formula. But on the other hand, you have also more information for the DN map, which is this quantity called the principal wave trace invariant, and it turns to be an important quantity here for to exploit. But you have to add this assumption. But on the other end, you have also more information with this term. So we will see now how to exploit that. So for conformal metric, the result that I will present now is for conformal metrics. Look, we consider the inverse problem for conformal metrics. So in a perfect world, we would like to have that if you take a conformal metric to G, then if the spectrum coincides, both metric coincide also on the whole manifold. This is in the in a perfect world, but of course, as we have mentioned, there is no reason for that to be true. So we have to look for a class of conformal. We are interested in establishing positive results, this time. So we have to look for a class of conformal metrics for which it is possible. And in that direction, I have established this boundary determination result. So okay, of course, to exploit the wave trace invariant, the wave trace formula, you have to assume that the boundary is Anosov with a simple length spectrum. And then also another condition that I had not been able to remove, because it's highly nonlinear, is to recovering this information here, that the conformal factor is 1 on the boundary. It's highly nonlinear, and actually the wave trace formula, it doesn't it's not useful here. It doesn't give any information on this term, on this principal term here, and we have no technique here, even for the Laplacian, to my knowledge. So we have to assume actually I can remove this assumption, but you have to add some strong geometric assumptions to do that. And this is just adaptation of some result that we have on the Laplacian case also. So we are stuck here. So we have to assume that the metric coincide at the boundary. And if you have that, then the Steklov spectrum determines the Taylor series at the boundary. And the 2D map coincide modulo a smoothing operator. So we work on in the boundary normal coordinates here. Okay, we will see after that. And as a corollary, we have if you add, of course, equivalently, we are able to recover to say that the Taylor series of the conformal factor is reduced to the constant function identically equal to 1. So the Taylor series at the boundary of the conformal factor is reduced to the constant function equal to 1. So if no difficulty if you add an analytic assumption on the conformal factor, and of course a real analytic structure on the manifold, and you can recover the conformal factor, knowing the the spectrum of the DN map. Okay, and one can also consider the linear problem for that. This is the approach of Guillemin and Cartan, who have considered isospectral deformations. So what is that? It consists in taking S infinitesimal rigidity. So you take a one parameter family of metrics, and which coincide with G at the initial time. And of course, it is called isospectral if the spectrum coincide for any S. So if you take this setting, this is the approach of Guillemin and Cartan for the Laplacian. Actually, you can linearize the problem. So we will refer this problem as the linearized problem, contrary to this problem, which is highly nonlinear. You have no parameter to linearize the problem. And so what we can establish is that if you take Steklov isospectral deformation of conformal metric, of course you have also this Anosov with simple length spectrum assumption, then you are able to get this that the conformal factor at the boundary is 1, okay, which is very difficult. Here it's very easy, it's the same way as for the Laplacian. It's very easy to do that with the parameter S, but here we must have this assumption because it is highly nonlinear. We are not able to do that without the parameter. And in addition to that, since we consider the DN map, we are able to obtain also that the normal derivative of the conformal factor at the boundary is 0, actually. So we will see how to do that. Actually, we will need the geodesic X-ray transform, but okay, not for symmetric tensors of high order, but only for functions which are zero tensors, of course. And we have so you integrate the geodesic X-ray transform. You integrate your function along every closed geodesics. Okay, and the proposition is that if you take a closed Anosov manifold, then you have the injectivity result of Dirichlet-Sharafutinov. You have also since then you have other proof of that, but you know this is pretty classic that you have injectivity of the X-ray transform for function on closed Anosov manifold, and this is what we will use. Okay. So the setting to prove the linear problem. Okay, we have these data here, and the observation of Duistermaat-Guillemin and Cartan was that if you consider the first variation of the metric, it is actually in the kernel of the X-ray transform. Okay, for symmetric two tensors here, but actually since we consider the formation of conformal metrics, then here it is reduced to consider the X-ray transform for function. And the function which is in the kernel of the X-ray transform is this one. And then we actually, of course, get that the conformal factor at the boundary is 1. Okay, so this observation is the key observation, and actually to prove that when you this is standard, you can use the trace formula to you know you have for any metric S you have a closed geodesics, and any closed geodesics for G deform smoothly as a closed geodesic for any metric GS, and this is standard that for example you can using the fact that the length spectrum is determined by the by the spectrum. This is you can prove that actually the marked length spectrum coincides for each metric, and actually this appears as a linearization of the marked length spectrum problem. You suppose that you have that the marked length spectrum coincide, and you differentiate with respect to the parameter S, and you get that by a standard computation you get that. This is exactly the linearization of the marked length spectrum problem. Then we can use the other invariant, the other spectral invariant, which is this one here, the principal wave trace invariant. So this exponential term, it's not 0 as we have noticed earlier. It's not 0 here for the DN map, so we can exploit that and say, okay, I have the same spectrum, so I have the same principal wave trace invariant, and so this term coincide. Okay, this is exactly the reasoning here, and we have to, of course, you know that the conformal factor is 1 on the boundary, so now any closed orbit. Any closed geodesics for one metric is also a closed geodesics for any other metric, you know. So you can say you know you say that the principal wave trace invariant coincide, and you put everything together in the other side, and you have that quantity is equal to 1. Okay, so now you have to be able to explicit a little bit this difference here of subprincipal symbol, and actually you can do that if you have that the boundary the conformal factor is 1 on the boundary, then the difference between the subprincipal symbol is up to a constant, the normal derivative at the boundary. So we will use that. And we have this parameter here, which saves us actually, because once again, we can differentiate with respect to S to linearize the problem. And once again, you have differentiating with respect to S, you have that this quantity here is in the kernel of the X-ray transform for function. And this is so you can use the injectivity of the X-ray transform for a function, which gives you actually that the normal derivative at the boundary is 0. Okay, so this is the proof. This is how we exploit the wave trace, the principal wave invariant. And as you will see, it's very easy with the parameter S. Okay, it linearizes completely the problem. So, but let's go back to the nonlinear problem here. So there it's much more complicated to establish this. We have two conformal metrics. We have no parameter S. Okay, you cannot differentiate. Okay, so the sketch of proof. Of course, we are looking since the DN map is a classical pseudo-differential operator, as we have seen. We can look at the symbolic calculus and look at the full symbol of the difference here, because we want to show that at some point we have to show that this operator, the difference, is smoothing. So to do that, we use the observation that if you have the same asymptotic expansions in the coordinate chart, then you just differ by a smoothing symbol, okay, or operator here. So you use this symbolic calculus here. You place in any coordinate chart for the moment, and you consider and you want to see that at any homogeneous order you coincide. If you can do that, then you will have that the symbol of this operator, the difference, is a smooth symbol. It's smoothing symbol. Okay, so the first step is to look at the principal level, of course. So we have seen that we have mentioned that this is actually very highly nonlinear. We can use there is no technique here. We can add some strong geometric assumption on the curvature, for example, to exploit the volume, which is a spectral invariant for the Laplacian and for the DN map. So for the DN map, the volume of the boundary is a spectral invariant. So this is we can use that spectral invariant by adding some strong geometric assumptions, but this is really not satisfying. The principal level, we have to assume that. At the other level, then you are able to linearize in some sense the problem. So as we have seen, at the subprincipal level, the difference between these subprincipal symbol is given by up to a constant by the normal derivative at the boundary. So what we have obtained is that here. So once again, you take that quantity, but you remove the S. In the nonlinear case, this is what we got. And then you are not able to differentiate. You have no parameter here. So we are stuck. But we can say that no, this time the X-ray transform is not 0 for every is not 0, but it's an integral multiple of 2 pi. So what can you say with this information? Is it enough to say something on the function f? And actually, yes, we did manage to show that. So just briefly some explanation. Okay, if you consider the projection here of the unit cotangent bubble, okay, you consider this projection, and then actually this is done by Lipschitz theory for transitive Anosov flows, which is the geodesic flow for Anosov manifold is a transitive Anosov flow. So you can use Lipschitz theory. Lipschitz theory. So the standard Lipschitz theory tells you that if you have this data, which is the X-ray transform is 0 over any closed geodesics, then the Lipschitz theorem tells you that this is a co-boundary in the sense that this is the Lie derivative of the, so this function seen as a function of the unit on the unit cotangent bundle is the Lie derivative in the direction of the geodesic flow of a certain function, smooth function U. And actually, we can adapt that by using the so-called non-abelian Lipschitz theory to prove that if you have this this information here, actually what you can prove is that it is equivalent to say that the function seen as a function of the unit cotangent bundle is not co-boundary, not exactly a co-boundary, but it's some kind of information. You can there is a smooth function with value in the unit disk, which verify this equation. So once again, you have this Lie derivative along in the direction of the geodesic flow, and this is what we use actually to prove that f is equal to 0. Here in the standard case, in the standard case, to prove that f is equal to 0, once you know that, it consists in using an L2 energy identity called the Pestov identity, and using this identity. So this is using this Pestov identity, you can show that knowing that you can show that f is equal to 0. And here this is much more complicated, but once you have that, actually you can also use some kind of a Pestov identity, but it's much more complicated to exploit. You have to work a little bit harder, but you can also use some kind of Pestov identity argument to show that f is equal to 0. So this is the same but much more complicated. And once you have that, then you can check on lower order terms, and actually we will reason by induction. When you say that every normal derivative, so you have to consider to fix a coordinate chart. So here we will work with boundary normal coordinates. Why? Because we want to exploit the exploit the computation of Lie and Ullmann, which have computed the full symbols of the DN map in suitable coordinates, and these suitable coordinates are boundary normal coordinates. So you have explicit formula, which are not so pretty, but you can use this formula in our setting. This is the setting of conformal metrics to get some information. So this is why we consider the boundary normal coordinates, because we have explicit formula of the full Taylor series of the full symbol of the DN map. And so we can see that if you reason by induction, so if you suppose that any normal derivative in boundary normal coordinates are 0 for any order less than j, then on the unit cotangent bundle, what you get is that the difference between this homogeneous term of order minus j are given up to a constant depending on n and j by the normal derivative at the boundary at order j plus 1. So you up to this point you can be convinced that you can get something interesting here. But to do that, I have formulated an adapted version of a trace formula of Guillemin and Duistermaat. So basically I found a paper of Guillemin from 1978, which considered much more the Laplacian with potential, so Schrödinger operator, and it has the he established a similar trace formula, but here it's much more general. So I have made this observation that maybe one can generalize what Guillemin has done for the Laplacian with potential, and to a more general setting. And this is what I have done. So to be able to consider this unitary, so this is about this trace here of the difference between this unitary operator of generated by a plus b and a. So you have also of course you have to, these operators have to be self-adjoint, because otherwise you don't have the Stone's theorem. You have to be able to construct this unitary group, and you have also you have to assume also that A is elliptic for the same kind of reason, and you have the same kind of trace formula that I have mentioned earlier, but for this quantity here, the difference between this quantity, and the difference is given by this term here, which is pretty standard. But we have seen this term appear previously, and you have also this term here, which appear, and so you have you can be convinced that if you can exploit this trace formula, then it will be a linear problem now, because you have this quantity here, which is linear. An integral, you will have an integral over closed geodesics, not an exponential. So it is much more convenient here. And so once again, you have this this is much more complicated, a little bit more complicated, but we are going to apply that to the DN map. So this is this Maslov index will be the Morse index, and etc. So this is I just wanted to have a pretty general setting. Okay, so the hard work has been done by Guillemin and Duistermaat-Guillemin, of course, which is so the hard work working on the Fourier integral operator and all the theory. The hard work is done by Guillemin. I just made an observation, and I have made this computation here. Okay, this is the only thing I have done is here. I nothing more. Okay, so to be exploit now we can exploit this formula. So once again, we are looking at the full symbol of the difference and the lower order terms in boundary normal coordinates. So I assume by induction that every normal derivative are 0 at the boundary with of order less than j, than fixed j. Then you have this quantity. You have this equality here on the unit cotangent below. So this is given by the normal derivative, as we have seen, at order j plus 1. So we have to be able to say that this is 0. To prove the theorem, we have to be able to say that this quantity is 0. So using that, you can see that if these normal derivatives are 0 for any order less than j, then the difference is an operator of order minus j, and then you are in the setting of this theorem here. Actually, one can apply to this theorem here to this is the next step, to consider it as a closed manifold. You consider the boundary, of course. And as operator A, you consider the DN map, which is a pseudo differential operator of order 1. And here, this is of order minus j. for j higher than 1. So you are exactly in this setting here. You can take a plus b, and you can take a is equal to lambda g and b is equal to lambda cj minus lambda g. And basically, what you obtain is that this integral here of the principal symbol of b is 0 along any closed b characteristic, which is here of course the closed geodesics on the boundary, since A is the end map. So just to explain a little bit, if you consider A plus B, of course you have here A plus B, you get lambda cj, okay. And if you assume that CG and G have the same Steklov spectrum, then this invariant is the same. And this is actually what we use to say, okay, these invariants are the same. So we have equality. Then we put everything, once again, we put everything on the same side. And so this quantity, this integral over closed geodesics. So also under the assumption that R is equal to 1, of course. So under the simple length spectrum assumption. Then what you get is that this integral here is 0 along any closed geodesics. And then you are back to the injectivity result of the injectivity property of the X-ray transform for functions because of that. Because the principal symbol of B, which is the difference, is given by the normal derivative at the boundary. So this is a function. This is a function. It does not depend on the xi variable. So you can use here. You have a real function, and you can use the injectivity result to conclude that that this is 0. Okay, and this is the end of the proof. You have proved that by induction that at any order you have and so for lower order terms you have linearized the problem using this adapted trace formula. Okay, and so this is the end of the proof, and okay, and you recover the normal derivative, and actually it is sufficient to have the full Taylor series of the conformal factor, and so you have the result. You have this result. You have shown this result here. Okay, the Taylor series at the boundary coincide, and of course the difference is between the two operators are smoothing. Okay, so last remark. We can also use this method. So this trace formula, we can use this formula in the same way to actually prove that one can recover also potential. If you consider the DN map with potential, and if you assume that the Steklov spectrum coincide for two different potential, then you are able to recover using this method. You are able to show that the two potential Q1 and Q2 have the same Taylor series at the boundary using the same method. Okay, this is closely related. This is even easier than the conformal case because the metric are the same in this case. You have just the potential which are different. Okay, this is the end of my talk, and this is based on the article, this article. Okay, and thank you for your attention.
Thank you very much, Florent. So we have time for questions. Does anyone have any? Please feel free to.
I have one. It's Colin de Verdière. Do you hear me?
Yes, we can hear you.
Okay, okay. It's a question about what you said on Morse indices, because I know if the metric has non-positive curvature, then the Morse indices vanish,
Mhm.
but you assume only another flow. And so it's really a general statement on another flow that the Morse indices vanish, or
Yes, I think. mm, I think it is enough to have an Anosov to if the manifold is an Anosov, then the Morse index is mm,
vanish.
yeah.
You have a reference for that? Or?
I think maybe I have in my paper I have a reference. This is probably. I'm not sure actually. You have this article of Duistermaat on the Morse index in variational calculus.
Yes, I know that paper, yeah.
And then
And so the Morse index for closed geodesic has two contributions. One is number of conjugate points, and the other
yes,
one is a contribution of the Poincaré map. So
yes,
already you have to have that there is no conjugate points. And I don't know that statement in general for another flows. But
okay.
it could be true, but I don't know it.
I think yes. So the Morse index is also the maximal dimension. I think I have to check.
Yeah,
If I give a reference of that.
yeah. But, because I don't remember that result.
Yes, I don't remember.
Okay.
Also.
Okay.
Yeah.
So I missed the beginning of your talk. So you assume that the conformal factor is already equal to 1 on the boundary or not?
Where?
The main result I miss. So
Yes.
you assume that already. Okay.
Yes.
That's the starting point. You cannot prove that, or
Yes. We can remove. We can remove that, but it's you have to add you have to add some strong assumption. This is so on the curvature. You have not really techniques to do that, to deal with that term, and this is annoying in this principle level. This is really annoying because every other term, it's you can.
yes, I know it's a starting point, so it's it's a problem. But okay.
But
On the
I
other
think
hand,
on the Laplacian you don't have such a result either, unless you assume some strong.
no.
You have some result, but if you have a negative scalar constant curvature, I think something like that.
Yeah. But I remember that there are some general results outside the conformal class for determining the metric inside, but up to gauge transform. But here you fix the conformal class, so probably there is no more gauge transform which are identity on the boundary zone. But I don't remember what is known in general. It's known probably for domains in the Euclidean space, but but I don't know what is known in. I don't remember what is known in general about determining the Taylor expansion of the metric at the boundary up to gauge transform.
Yeah.
Which could be the identity and the the metric are the same at the boundary. Okay, but I don't remember. But maybe you know that.
No, actually, no.
Okay,
Actually.
okay, because then it's a different viewpoint which says that you are no more once you fix the conformal class, you are no more way to have a gauge transform. So it becomes rigid in some sense.
Yes.
You understand what I say? It's okay. Okay. Okay, so thank you for
Thank you.
Okay, great. Thank you, Yves, for all the questions. Do we have any other questions in the audience? If not, we can thank the speaker again.
I think there's
Sorry,
a question in
I didn't
there's
see Marcello.
Yeah, and there's a question in chat after that, Laura.
Oh, there is a...
Yeah, I think there was a question.
Oh, interesting. I do not see it actually. There it is. Okay, so Louis Biapou is asking if the expansion or contraction rates of the Anosov flow are relevant in the length spectrum.
Sorry, I didn't.
So the question is in the chat if you manage to see it. So they're asking if the expansion or contraction rates of the Anosov flow are relevant in the length spectrum.
Okay. No, I don't think so. No. I think.
I don't understand the question, but already the Poincaré map, which is in the trace formula, gives some information on the expansion along the closed geodesics. And if we iterate, it gives some information on the question is, can you detect the Lyapunov exponent or something like that from the spectrum? That's a general question, independent of Dirichlet-to-Neumann.
Yeah.
I don't know the answer. I don't know. Maybe if you have some, I don't know.
Completely different question. Yeah.
That's a very interesting question. Can you extract from the trace formula or from something else the Lyapunov exponent on at least an upper bound?
I think this is an open question. This is
if you know the Lyapunov exponent along all closed geodesics, you know it's Anosov, it should say something because they are dense in the phase. I mean, you can approach every long time geodesic by closed geodesics. So
yes,
probably the upper bound is already given from what you see on closed geodesics. Not sure. It's a bit intuitive. It's not.
Yeah.
Okay, thank you. And I think Marcello also had a question.
Thank you very much. First of all, thank you for your talk. Can you hear me properly?
Yes.
Oh, perfect.
Thank you.
I saw that you said yourself in the case of a smooth manifold. I mean, there are some recent works, for example, in my mind, there is the one by Protorovich, Farnowski, and Levitin, in which actually they study the case of no-smooth, let's say, domains in that case. So I was wondering if actually you can somehow understand something also of the regularity of your manifold, if you thought that this problem, I mean, of the regularity of the manifold from the study of the singularities of the trace.
Okay, you want to remove some regularity?
Yeah, let's consider for a manifold that is no more smooth. Let's say it's a compact Riemannian manifold, well, a compact manifold which is no more smooth. Let's say, can you say something about the regularity? Well, can you characterize the regularity starting from the trace or the singularity of the trace?
Actually, if you
Sorry, it was just a curiosity. I mean, I saw that actually your setting is different, but it was just a curiosity to know thought about using these techniques for?
No. And if you consider okay, no. I think
Okay, thank you very much. Thank you very much.
No, but that's a very interesting question. If the metric is enough smooth, say CK for some K, what value of K you need in order to have singularities modulo, I mean, what you say, like some Dirac meshes at plus some, say, more regular term, but without a full asymptotic expansion. I mean, probably if the metric is CK for K, maybe depending on the dimension, it's more or less clear that you get some trace formula, but not with a smooth remainder.
yeah.
In particular, the length spectra are determined. It's probably enough that the metric is CK. The problem is that you have to control the techniques of Fourier integral operator. Usually people say you have to use only smooth objects, but it's not. It's just because it's much easier. But in fact, smooth means CK for K large enough.
Yeah.
Okay, that's but the explicit value of K, it's really a difficult problem.
Yeah.
Thank you very much. Yeah, thank you very much indeed.
Okay.
Thank you. Yeah.
And okay, you have already that the main term in your trace formula, you have to ask that they are already well defined. I mean, in particular, the Poincaré map. The closed geodesic, they are defined by just, there is no need of regularity. But the Poincaré map needs a bit of, and the same for example, for Anosov flow. For being Anosov, usually you start with smooth
flow, yeah.
data, but what it's not a CK for K large enough, and then probably. But I don't know. I don't know the answer. Okay.
Yeah.
Thank you very much indeed. Yeah, just I was wondering just because there were some papers in which they study this kind of problem, and now it seems that the Dirichlet-to-Neumann was quite sensitive respect to the regularity, but yeah, it was a different frame because in that case were only two-dimensional domains, so actually it was a completely different setting. So I was wondering if actually there was some connection with this setting. Thank you very much for your.
In two dimension, there were already a lecture in this seminar on the case with corners, as far as I remember. I don't remember who gave a talk on that, but there was something.
And the Steklov inverse problem in the two-dimensional case, yeah, I didn't mention, but yeah, usually the two-dimensional case is pretty yeah, you have different techniques to, but here I'm not sure it is for two-dimensional manifold.
No, but the case with corners, it's already something.
I mean, in the two-dimensional case, as soon as the conformal factor is one at the boundary, it's isospectral, right? So
yes, you have this conformal invariant.
So that from that condition, it makes the problem not make sense anyways, right?
That condition, but you have to work for general metric.
Yes, of course.
Yes.
Okay, well, I think we can thank the speaker again. We can always keep chatting anyway. I'm not throwing anyone out. So thank you again for the great talk and the lively conversation we had afterwards. We'll meet again next week with a talk by Fanuel Mariano, who will talk to us about a conjecture of a polyar functional for triangles and rectangles. In the meantime, have a lovely week.